Chapter 4 in Anton is titled General Vector Spaces, and in this short video I just wanted to give a warning as to this chapter is a little bit more difficult than the preceding chapters, and that's because there's a significant jump in abstraction in this chapter. And what do I mean by that? Well, recall when you were first learning about numbers. First, maybe you learned about positive integers, 1, 2, 3, and so forth, and then someday you probably don't even remember you were introduced to negative numbers, and that took a little bit of getting used to. And that's what I mean by a jump in abstraction. You can't easily visualize -2 cats, for example. Then one day, you're introduced to fractions, and that also is a little bit of a jump in abstraction, presumably. And then also after that was real numbers, although even between there's some things like square root of 2 and so on. And then maybe you've been introduced to complex numbers, or maybe you haven't. Later on in this course, we'll see complex numbers. Then another situation where there's been a jump in abstraction that you've already been exposed to is algebra. First we were talking about numbers like 2, 3, and 4, and then eventually in an algebra course, they replace these numbers by variables like x and y. So that's an instance of a jump in abstraction, and once you got used to it, it was no big deal. Similarly, in calculus, there is a jump in abstraction from what I'm calling the discrete to the continuous, involving things like infinitesimal and limits. Now let's move on to linear algebra this course, and let's look at the jumps in abstraction we've seen so far. So we've started considering vectors as arrows in R2, starting at one point and ending at another. And then we identify these vectors with a pair of numbers. And so that was giving R2. And then we said, well, the same thing could be done in R3. And then even in Rn. So elements of Rn are n tuples, or n numbers ordered. And then we talked about the standard basis vectors and coordinates, these v1 to vn, those are the coordinates of a vector v. And then in this chapter 4, we're going to start with an abstract or general vector space v, and it's modeled on Rn. So an element of v is called a vector, and v is just a set with a couple of operations, which we'll talk about, vector addition and scalar multiplication. Just like you can add vectors and multiply a scalar and a vector when the vector is in Rn. Then there's going to be something called the dimension of a vector space. That's basically this n here. We've got a basis, a notion of a basis, a span, and a subspace. And then later on we'll also consider maps between two vector spaces. All this abstract situation is really modeling the concrete situation of Rn, very similar to how a variable x models a specific number like 2 and 3. Now the good news is that when we move on to chapter 4, 5, and 6, and so on, things get back to being a little bit easier in abstraction. And then one other point I should have mentioned is that a finite dimensional vector space, V, together with a choice of bases, is Rn, or is isomorphic to Rn. And so this case, thinking about this case of Rn, really is the main case of interest in this course.